A single attention head can spread weight across this entire sentence. Its limitation is subtler. For each query, it produces one routing pattern in one learned space. When Maya handed the violin to Noor, she tuned it before the concert. Focus on the word tuned. It sits inside several relationships at once. She tells us who performs the action. Violin is the object being discussed. Noor and Maya help establish the earlier event and the likely reference of she. In the previous episode, one attention head built one set of weights for a query and used those weights to mix value vectors. That head could spread attention across every visible token. It was not limited to one word or even one idea, but it still produced one routing pattern for tuned inside one learned query and key space. The same weight assigned to Maya scales every dimension of Maya's projected value inside that head. The same is true for she, violin, and the rest. That is the pressure point. Language can contain several useful relationships at the same moment, while one head supplies one pattern for moving information between positions. Transformers do not solve this by making one enormous attention map. They run several smaller attention operations in parallel. The reason this works is more interesting than giving each head a neat label. Keep the sentence in place and select tuned again. For one attention head, the model produces queries, keys, and values through three learned matrices. Multi-head attention gives each head its own versions of those matrices. The full token representations are projected into a learned coordinate space for head 1, often a narrower space in standard designs. A different set of learned projections creates the space for head 2. Then head 3 gets another set. These are not pre-cut boxes marked grammar, reference, and meaning. Each projection can mix coordinates from the full input representation. Two heads can even learn overlapping spaces. What changes is the geometry. In one projected space, the query from tuned may align strongly with the key from she. In another, it may align more strongly with violin. A third may produce a broader pattern involving several nearby tokens. These are schematic examples, not measurements from a trained model. The point is that different learned projections can make different relationships easy to express. Each head now runs the attention operation from episode 4. Compare the query with keys, normalize the scores, then use those weights to mix that head's projected values. The operation is familiar, but each head gets a different learned coordinate system. Now place the heads side by side. Head 1 produces one attention row for tuned. Head 2 produces another. Head 3 produces a third. Because their query and key projections differ, the rows do not have to agree. Their value projections differ too. Even if two heads happen to place similar weights on the same token positions, they may carry different projected information along those routes. This is the advantage a single head cannot reproduce in the same form. One head can create a complicated mixture, but it cannot produce several independently learned routing distributions for the same query and preserve all of their value mixtures as separate channels at that point in the layer. The original Transformer paper described this as attending to information from different representation subspaces at different positions. Its base model used 8 heads. Each head was narrower, so the total computational cost was similar to one full-width attention head in that design. 8 is not a magic number. Modern architectures use different counts and sometimes different ways of sharing keys or values. The lasting idea is parallelism. Several learned routing views can exist before the layer commits to one combined output. Our 3 visible heads are only a readable sketch. A real model may have many more, and some of their maps may look almost identical. That raises the next question. Once the heads disagree, what does the transformer do with all those answers? The transformer neither averages their attention maps nor selects a winning head. For the token tuned, each head produces its own output vector, the weighted mixture of projected values from that head. Think of those outputs as narrow colored strips. One strip arrives from each parallel route. The transformer places the strips side by side. That operation is concatenation. Nothing has been blended yet. The boundaries between the head outputs are still intact. Then, the combined strip passes through one learned output projection, usually written as WO. This linear map mixes information across the concatenated channels and returns a vector in the model's working dimension. Only now do the parallel routes become one output for tuned. The compact formula says exactly that. Each head applies attention to its own projected queries, keys, and values. Multi-head attention concatenates those head outputs and multiplies by the learned output matrix. There is no referee inside WO that understands which head found grammar or meaning. It is a learned linear transformation. The heads compute independently inside this attention operation, and the output projection recombines their channels. That gives us the architectural answer to the title. Several routing patterns are useful because the layer can preserve several different mixtures long enough to combine them, instead of forcing every useful relationship through one set of weights. But a clean architecture diagram can tempt us into a false story about what the heads learn. Training never hands out job descriptions. Still, when researchers inspect trained models, some attention heads do show recognizable patterns. In one analysis of BERT, particular heads often attended to fixed relative positions. Others aligned with certain syntactic dependencies or coreference relationships. Work on neural machine translation also found important heads with positional and syntactic behavior. That makes intuitive sense. Independent projections give specialization room to emerge, but the word particular matters. These observations belong to specific models, layers, tasks, and analysis methods. There is no universal head number that always tracks pronouns, syntax, or the previous token. Some heads spread attention broadly. Some focus on special tokens. Some repeat patterns already visible elsewhere. An attention map is also not a complete explanation of a prediction. It shows the weights used by that attention operation. It does not, by itself, prove that one head caused the model's final answer, or that all information about a relationship lives in that head. The safe picture is a collection of learned routes, not a row of tiny experts with permanent skills. Some routes become interpretable, others overlap or remain hard to name. Pruning experiments make the picture messier. Researchers have removed attention heads from trained models to see what breaks. In one English to Russian translation experiment, 38 of 48 encoder heads were pruned with only a 0.15 blue drop. Other experiments found that many individual heads could be removed with little effect, and that some layers could be reduced to a single head. Remove enough heads across the network, though, and performance can collapse. The result depends on the model, task, layer, and pruning method. This does not show that multi-head attention was pointless. These models were trained with many heads before researchers removed them. Extra heads may provide room for useful specialization, overlapping solutions, and flexibility while the model learns. After training, several routes may end up doing similar work. That is why the title needs a precise answer. Transformers need multiple attention heads as an architectural way to offer several independently learned routing views and value mixtures at the same time. They do not need a mythology where every head owns one concept and every head is irreplaceable. Return to tuned. Several projected spaces produced several routing patterns. Each head built its own value mixture. Concatenation preserved those mixtures. The output projection merged them into one updated contextual vector. Several views have now become one result, and even that result is only part of the machine. Attention still has to work alongside residual paths, normalization, and a feed-forward network, then repeat across many layers. That complete system is the transformer block. It is the next episode, and it explains why attention alone is not all an LLM needs.